Okay, so if you're in here, you should be looking to learn about Python and drones. We're going to be using drones as an educational tool to learn intermediate Python constructs. So briefly introduce myself. My name is Matt Harrison. I've been using Python professionally since 2000. I run a company that does consulting and corporate training called Metasnake, and we do Python and data science type stuff. My blog there is harrysun.com, my company Metasnake if you're interested in that. I've also written a couple books on Python, so beginning and intermediate Python. So what we're going to be talking about today is going to cover a lot of these intermediate guys here. And I actually just ran a Kickstarter a couple weeks ago for a thing that I'm launching called PyCast, which is going to be a subscription service to data science and Python screencasts, so weekly screencasts on those subjects. So if you're interested in that, the Kickstarter just ended, but I'll be launching the beta here pretty soon. So that's pycast.io. Check that out if you're interested. And if you're interested in me personally, I guess, or just what I tweet, my handle is dundermharrison, __M Harrison. Okay, so anyway, that's enough about me. We'll talk about intermediate Python. So I guess I would say, like, let's just get the lay of the land here. Who in here is like a programmer? Their title is programmer. Okay, so maybe half. Who in here is, what else do we have? Scientist. So who here is some sort of non-data scientist, but a scientist? Okay, so what kind of scientist? Physics?
Remote sensing.
Remote sensing. What's that? Geophysics. Okay. And then we have, who in here is a data scientist? Raise your hand. Okay, a couple of those. Okay, who are we missing?
Engineer.
Engineer? What kind of engineer?
Electrical. I write programs and do data analysis and stuff. So
Okay.
somewhere in there.
Okay.
Telecom.
Telecom?
Robotics.
Okay, robotics. Okay, so people who are using the traditional scientific stack in Python, presumably. And I'm not going to talk about the scientific stack in Python. So if you came in here hoping to make NumPy run 5 times as fast or write optimized Python code, you're in the wrong class. I apologize for that. The purpose of this class is to teach some of the nicer things, fancier stuff with Python that I think makes Python a fun language in pure Python itself. Some of these may be applicable in, scientific type stuff. Some of them may not. But if you're in Python land long enough, you're going to see some of them. So I think that you might, if you're doing Python for a long time, you might either be bored by typing things out a lot, repeating yourself a lot. You might be confused by code that you find in the wild, like a decorator, or you might just be doing things that are less efficient in pure Python world. So let's do another raise of hands here. Who here has used a decorator before? Okay, of those who have used a decorator, who's written a decorator? Okay, a couple of you, okay. Who here has used generators before? Okay, cool. Context managers? Written context managers?
Is that like with something?
Uh-huh.
Something?
Yeah, so there's using it and then there's writing one, okay. Okay, so people who kept their hands raised the whole time, you can be like my tutors and you can help me do that, teach other people. But that's what we're going to be talking about. These fancier constructs in Python that make programming in Python, I think, fun, but could be confusing to people who haven't learned these things before. So I'm going to assume basic Python knowledge. I'm going to assume that you have Python installed on your laptop, either Python 2 or 3. The assignment will work with either, so it doesn't matter. And basically, we'll talk about some of these things, and then we'll do a demo and an assignment, and then we'll just repeat. So Again, Python 2 or 3, this is agnostic. For the purposes of this course, there are some differences between Python 2 and 3, and I'll cover those differences. I guess just for another lay of the land, who here is using Python 3? Okay, that's a lot more than I expected. Okay, cool. Okay, basic outline. I'll talk about drones. We'll talk about functional programming, dive into functions a little bit more, talk about decorators, class decorators. Then we'll get into how to do iteration in Python, and we'll talk about generators and context managers. So drones. These are drones. I was just in Yellowstone National Park last week, and all over the place they have signs that say, "No drones allowed." Which, so I live in Utah, and I go to Arches or wherever all the time, and I thought, oh, that's sort of silly, right? Like, you can't have a drone in Arches and get like cool pictures of Arches or whatever, fly up to them. But then I was in Yellowstone, and all of a sudden these random geysers would be like spurting up all over the place. And I'm like, that would be a disaster with drones, because you'd have 5,000 drones flying around, getting shot down and landing and stuff. Anyway, so I guess I appreciate that. But it's an interesting world that we live in, where these things, there's actually signs at national parks that say, no, I think it said unmanned flying vehicles. So this is an unmanned flying vehicle. So I think drones are fun, they're easy, they're cheapish. This guy here costs, this is an AR drone, it's 3 or 4 years old, and it costs $300. So somewhat affordable. You can get cheaper ones. My interest in drones came from a class I was teaching. So at my kids' school, I do an 8-week class every year. Parents can come in and teach an 8-week class on something. So I've done programming, and I've done like ebook creation and HTML. I wanted to revisit programming again, but in this day of iPads and multi-million-dollar games, when I started programming, it was on the Commodore 64, and you boot it up, and you're in this basic prompt, and you typed in things, and you made like really crappy ASCII art. But that's just not available today, right? I turn on my phone, and I don't have a prompt there. I turn on my iPad, there's no prompt there. So I wanted to teach programming to kids that are like used to, I don't know, FIFA, Temple Run, whatever, silly game, Minecraft sort of things. So, something that would be a little bit more hands-on. So what I did was I taught Python, and instead of just talking about Python, we talked about how we would control a drone using Python. And then we went out and we actually ran programs and flew this drone around. And so here, this is an actual picture of the kids chasing after this drone after they wrote a program. So I guess I would say also, I'm not like a super drone enthusiast. If you want to ask me like what kind of processor this drone has and the technical specs of it, I can't answer those questions for you. I'll say Google that. But I come to this more from an educational point of view, where I think this is a cool tool that allows me to show some programming concepts and let kids understand them and grasp them and see, oh, wow, I can, rather than just putting text on a screen, I can actually control something in real life by writing a program. So this is, again, as I said, this is an AR drone. This is called the Parrot. Or Parrot's the manufacturer. This is called the AR Drone 2. It's 3 or 4 years old. There's various projects here that support, try and stay close to the mic, various projects that support this. So there's Python interfaces to this. When you plug this in, you connect the battery here. It starts a Wi-Fi hotspot, and then you connect to this Wi-Fi hotspot, and then you push data down your connection there, and that tells us what to do. So this Venther Python AR drone is one. I've got another one here called PS drone that is a fork of a German guy's master's project that I'm using for other reasons that basically the same, but has code that isn't PEP compliant and whatnot in there. And that's his link down at the bottom, playsheep.de. So he's got some code in there, and I've forked that and put it in GitHub because it wasn't in GitHub. Any other interesting things about this? So this guy has a camera on the front, so you can install your iPhone app or your Android app or whatever, and then you connect your phone or your device to this, and you can have like a first-person drone flying around and looking at it. It's got a USB connection here, so you can put in a flash drive, and then it can record, so you can be like the ultimate creepy voyeur or something and fly this around and take pictures with it. So that's AR drone. And the code to fly it's actually pretty straightforward. So I do something like this. I import this module, PS drone. I import time because a lot of things you have to put in delays. And then I create an instance of this drone, and that does all the connection. And I say take off, and it sort of starts running the propellers. And I say time sleep. And what that time sleep does is that gives it actual, it takes about 7 seconds for this guy to like lift off the ground. So if I don't put that sleep in there, you say take off, it sort of like does something and then immediately lands. So, whoops. So we need to put in some delay in there. And then I say shut down, and it turns it off. So pretty straightforward. I mean, that's your hello world for droning with this guy. I guess sort of summarize like the AR drone, the pros of it, it's available. You know, you can get this on Amazon and have it in your house in 2 days, right? It's pretty programmable. I'd say it's somewhat pricey. I mean, it's affordable, but like I'm kind of reticent to let a bunch of fourth graders fly it around just for fun without my supervision, right? It's a $300-400 device. It can be a little finicky, durability. So this hole right here is called the exterior hole. I have an interior hole that has like guards around these guys that didn't fit in my suitcase. So we're flying exterior mode here. So everyone signed the NDA, right? If the drone comes over and chops your head off or something. Okay, good. And like I said, this guy's 3 years old. There's actually a newer model of AR drone. Last time I checked, it didn't have a Python interface. It might now. There's like DIY drones, which is this big spot for people who are aficionados of droning and sort of building your own drone and whatnot, where you can go read their forums and geek out on that stuff. Like I said, my interest in drones is more as an educational tool rather than geeking out on them. Okay, I also have another drone up here. This guy right here, this is a little nano drone. This is called the Crazyflie. This is basically like an Arduino with wings. So it's also somewhat controlled by Python. I say somewhat because, as you can see, I've got this like tether on it right here. So I got this to mess around with, but it turns out that one of the nice things about this guy is that he's got some sensors on the bottom here that tell him where he is relative to the ground. And this guy doesn't have any sensors on the bottom. So how people control these guys, and if you like Google around on YouTube, you'll see like people using like PS3 controllers and just really fine feedback. So basically it's like you're doing like a PID controller feedback system all the time with your PS3 controller to control this. Yeah, this guy has like a USB radio that you plug into your laptop. He doesn't set up a Wi-Fi hotspot. But these guys go, I think, 30 miles an hour. So people do crazy things with these. And like I said, it's extensible, open source. It's got a bunch of expansion ports on the bottom here if you want to geek out about those sorts of things. I'm not going to fly that because I'm not very good with it. Okay, and then Turtle. Turtle, who here's used Logo or Turtle before? Okay, so sort of a classic thing from the 60s era. So basically Python comes with this thing called Turtle. it allows you to control this turtle and make it move around and draw shapes. So what I've done is I've taken this PS drone interface and I've wrapped turtle with it. So we can basically write code that will run as turtle, but will also control the drone as well, just changing which class we pass into. So, yeah, so there's this TPS drone module in the repository, and if you import that, you can create this drone, and you can take it off, and then you can do commands, and you can sleep if you want to sleep, but it's not really necessary for the turtle guy, unlike the real guy. And you'll get something that looks like this. It will draw some shapes around. Commands for our class that are interesting: take off, which says launch basically, land, and then there's a bunch of move commands. So and these are, let's go over to the microphone. Like I said, I'm using this German guy's code, and doesn't follow PEP 8, so these are camel case Java conventions. So move capital left, move right, move up, move down. Set speed changes the speed of the drone, and I've got in the turtle guy, I've got a guy called write that will write text out to the actual turtle screen. The drone doesn't write any text. I guess I could hook up some smoke or a laser system or something to make him write, but I haven't done that. Okay, so that's an intro to the drones. As we do the assignments, I'll try and make the drone do some of the assignments, and you guys get to actually use Turtle to do the assignments, and then if we have time at the end, I'll let people write code and run it on this guy at the end. So, any questions? People who came in late, this is the link for the code, and there's some handouts down here that we can get. You can come down and get during our first lab here. Okay, now we'll jump back to Python for a minute. So Python is a multi-paradigmatic language. Many languages are strictly imperative or object-oriented or functional. Python supports many of these styles of programming. So imperative programming, if you're not familiar with that, is using statements to change how a program behaves. This would be like BASIC. And here's an example of using imperative programming to sum some numbers. I create some variable, and I tell the program to iterate over some numbers and increment that variable, and then I can print out the total. That would be an imperative way of doing that. There's another style of programming called object-oriented programming, where we create classes and instances of these classes, and then we call methods on these to mutate state and whatnot. So this would be an example of using an object to sum numbers here. So I make this class called summer. In its constructor, I have an attribute called sum that I set to 0, and I define a method called add that takes a number and adds it to the sum. And then I'm just going to create an instance of it. I'll loop over some numbers, and I'll call the method, and then I can ask summer what his sum is, and he prints it out. So that's object-oriented programming. There's also what's called declarative programming, and SQL is an example of declarative programming, where in declarative programming we don't say how we're going to do something, we just say what we're going to do. So I just want you to select everything from the sales table where the store is 5. I'm not saying loop over every row in this table and look at store ID and assert that it's 5 and collect those and that. I'm just saying this is what I want you to do, and the database engine behind the scenes figures out, the query planner figures out something to do and goes and executes that. And this is sort of similar to functional programming. Who here has done Lisp or some functional programming here before? Okay, so what do we have? Haskell? What do you guys use? Clojure? Okay, anything else? Scheme? Scala? Okay. Okay, so some of you are familiar with functional constructs. And functional programming is somewhat vague, and people like to define it in different ways. So one definition here is that instead of using objects to hold state, you call functions, and you try and avoid mutable state, and you try and avoid side effects. And we'll look at some examples of like functional programming. So here, this would be an example of summing those numbers using a functional programming construct. And here we would call a reduce function that's built in Python. And we're going to say, I'm going to call this reduce function with this operator add. So this basically this is a function in Python that takes two parameters and returns the sum of them. So it's going to take two things, and you're going to sum up everything in range of 10, and you get 45. So this is 2 lines of code versus whatever, 8 lines of code here. So somewhat straightforward if you're used to reading that style. In practice, you'd do something like this. You just call the built-in sum function with range of 10. And so one can wax on about the virtues of functional programming and whether it reduces bugs or whatnot. I'll try not to get too much into that here. But functional programming came out in Python in 1.4. This is actually an old feature of Python. And in Python 1.4, there are various functions that were built in, and the Lambda statement came out. So we'll look at those. So again, we said functional programming. You call functions, and you try to avoid keeping track of state and side effects, immutable data, and whatnot. So we'll skip that. Okay, so one of the things that's interesting about functional programming, or one of these notions that's found in functional programming, is what's called a first-class function. And that's the idea that a function is not something you just call. You can actually pass a function around. And if you're coming from like a Java land, this might be a little weird. Like Java, you basically call methods, but you don't do much else with them. In Python, you can call functions, you can call methods, you can also pass those functions and methods around. Another notion of functional programming is what's called higher order functions. So a higher order function is similar to this reduce function that we saw earlier. A higher order function takes a function as input or returns a function as output. And again, if you're coming from Java land, that might be a little weird because that's not really possible in Java land. We'll see some examples of that too. Another notion of functional programming is what's called pure functions. And this is the idea that a function calls idempotent, and every time you call it, you're going to get the same result. And there aren't side effects. So side effect would be like writing something out to disk, changing some state somewhere, something like that. So a pure function, there's the math module in Python, and so the cosine COS function in there is a pure function. Every time you pass in some number to cosine, it better give you back the same answer that it gave before. If not, something's wrong in the space-time continuum or your cosine library. Impure functions, print is considered an impure statement. In Python 3, it's a function because it has a side effect. It actually writes something to standard out, which is considered a side effect in functional terms. Random, the random function in the random module is also impure because every time you call it, it should return a different number. So by nature, it's impure. Okay, so Lambda is one of these guys that came out in Python 1.4. Who here has used Lambda before? Okay, some of you. We'll cover it briefly here. Basically, what Lambda allows you to do is create a simple one-line anonymous function. So here I'm defining a normal function in Python, mul, that takes two parameters and returns the product of them. And here I'm defining what's called a Lambda function. So I'm assigning mul underscore 2 to this Lambda statement here. It says Lambda a comma b colon. So a and b are these parameters into this anonymous function. What comes after the colon is the result, what it returns. So it's going to return a star b. And sure enough, if I type this into an interpreter, I can say mul2 45 equals mul 45, and I get true. So that's how you make a Lambda statement. You just give it the parameters, the parameter list, colon, and what you want to return there. Where you see this mostly used in Python land is when you're sorting. You can use it as a function for the key or CMP parameters for sorting. You'll also see it in callbacks used for like GUI toolkits. So here's an example of sorting. So here I'm going to say I've got some data here. It's in a string, and I'm going to split it. So this should give me a list of string numbers. If I call sorted on that, it sorts them in lexicographical order, which maybe we want this 100 to come at the end here, but we want to keep it as strings. So we can do something like this. We can say sorted. We're going to sort data, but rather than sort it on the values that are passed in, when we pass in this key parameter, it tells Python, I want you to sort it based on the result of calling this function with one of the parameters passed in. So here our guy says, you're going to take in some item here, and you're going to return the integer value of that. And lo and behold, when I do that, I get these in a numerical sort order, but I still get back the string results. So just a hint in Python, there's also a CMP function that's an option for sorted that takes two parameters. General knowledge in Python land is use key, not CMP. It's slightly faster, and they do the same. They can do the same thing. Okay, one thing that gets people hung up with lambdas is that they don't support statements in them. So if I want to put some if statement in my lambda function, it's a little bit hard to do. So here I'm just saying I want to make a function that takes some parameter x, and if it's greater than or equal to 0, I want to return pos, otherwise I want to return negative, presumably. I start typing this out, and I put this if statement in here, and I put the colon, and then I hit enter, and I get a trace back here, and it says invalid syntax error. And that might be confusing for people who are new to Python who are trying to put just random statements into lambdas. But the crux of the problem is that lambdas don't allow statements in their body. They only allow what Python calls an expression. So if is a statement. Python has this notion of an expression, an expression that supports creating an if-else, but an expression, not a statement. So basically, I can say something like this. I want you to return the string pos if x greater than or equal to 0, else return neg. This right here is an expression. It's not a statement. And so this actually works, and I can call it with that. So lambdas in this sense are crippled in that they don't support statements. And so you get people don't like them, and people complain about them. And if you're confused, if you don't know the difference between an expression and a statement, a simple rule to help you remember them is something that can something that you would return in a function is an expression. So I wouldn't return an if statement here, but I would return a number, or I could return this whole expression right here. And here's an example from the standard library. There's a library called cookielib.py, and it's just sorting here. So it's saying I'm going to sort my cookies, and I want you to sort them based on the length of the path attribute of my cookies. So presumably inside of your cookies, there's this path attribute. It's going to sort them based on length, and it's going to reverse them. So the longest path will come first. Okay, so in summary, Lambda expressions are good for one-liners, but not much else. But people who are used to Clojure or whatnot, or Lisp or Scheme, see Lambda all over the place and think, oh, you have to use Lambda everywhere. Which in Python land doesn't really work super well. Okay, another functional construct in Python is map. So this is what we call this higher order function. Again, higher order function is a function that either takes a function as input or returns a function as output. So map takes a function as the first parameter, and it's going to call that function on every item of the sequence here. So we've got some integers in a list, and it's just going to call stir on them and convert them to stir. This is Python 2. So we can also pass in Lambda statements here. So in addition to normal functions, we can pass in lambda functions. So this guy is going to return true or false depending on if x is greater than or equal to 0. And if we map that over this sequence of integers, so we get false, true, true, true. So -1 is not greater than or equal to 0. All the others are. And here's an example from the standard library in the tar file guy. So there's a module in Python that helps you deal with tar files. And one of the methods on that is called nameList, and it has a map in there, and it says, to get a name list, I want you to iterate over the info list, and I want you to return the name attribute from everything in the info list, and that gives you the name list. Okay, so I said I would discuss the differences between Python 2 and 3. In Python 3, there was actually sort of a skirmish about removing functional programming constructs completely from Python 2, or from Python 3, because one of the notions of Python 3 was that it was going to clean up the language and remove warts and whatnot, and a lot of people are like, functional programming itself is a wart, and other people are like, if you remove functional programming, the world will end. And in the end, functional programming constructs sort of stayed in Python 3. So one of the notions, though, another notion of Python 3 is that Python 3 is sort of lazy by default and doesn't materialize things ahead of time. So in Python 3, map is not a function, but it's a lazy class. And when you invoke map in Python 3, so here I'm going to map stir to range of 10, instead of getting a materialized list back that has all those items in it, I get this map object, which is an iterable object, and we'll talk about what that means in iterators and iterables in later here. But if I call next on underscore, underscore, if you're not familiar, is the result of the last invocation of the interpreter, I get the string 0. So if I actually iterate over this guy, then it materializes as I iterate over it. Okay, so one of the nice things about this in Python 3 is that because this is lazy, you can feed into it an infinite sequence. In Python 2, if you fed an infinite sequence into map, it would take a really long time to return the result. Python 3 will return your result, and you can consume that as you want. If you really want to mess with infinite sequences and maps, you can actually do that in Python 2, but you have to use the built-in IMAP guy found in itertools, which is in the standard library in Python. Okay, another 1.4 feature of Python is this reduce function. And again, if you're doing like Clojure or Lisp, you'll see this all over the place. Basically, what reduce does is it's a higher order function, so it takes a function as input. The first function that it takes as input takes 2 parameters, and it calls those parameters first on the first 2 guys in there, and then with the result of that, it calls it with the result and the next guy, and the result of that with the next guy. So this guy's taking the product of all these guys, so it's doing 1 times 2, and taking the result of that times 3 times 4. So you get 24. That's how reduce works. In Python 3, reduce was not removed from the language. It was kept in there. But it was moved to this functools module, so it's not in the built-in namespace in Python 3. And unlike map, it's still a function, and it's not lazy in Python 3. Here's an example from csv.py in Python 2, and this might be an example of why people wanted to remove reduce. So if you look at this, this guy, quote char, says the quote character, so this is the CSV, comma-separated value parsing library in Python in the standard library. The quote character is the character that's used to quote columns or whatnot. So this is how it's guessing the quote character. It's calling reduce over quotes.keys. So presumably there's some map that has some keys. And this map actually maps the characters to the count of times that character appeared in a line. And the function that's passed in is this lambda statement here, lambda a, b, and using a named parameter to pass quotes into that. And it says quotes a greater than quotes b and a or b. So I don't know. If you look at that, can you tell me what that does? Is Python supposed to be a readable language? This one takes me a minute to parse. This is actually what this is doing. This is the logic of what it's doing down here. It's saying if quotes A, if the count of the characters in A are greater than the count of characters in B, I want you to return A. Basically, the heuristic is look for the character that has the most appearances in a line, and that's the quote character because it's coming before every character and before and after every column name. So if the count of A is greater than B, return A, otherwise return B. So it's doing some short-circuiting with the and or to be cute. So for some people that's readable, for some people it might not be. Python 3 actually changed this, and this is how it guesses the quote character. So it uses the built-in max function. It says, I want you to take the max of quotes, and how I want you to determine max is call the get method on quotes, which will take the result of invoking get with that guy and give you the count and return the max of those. So slightly more readable. This is also functional in nature, but using abstraction with the max function. So I think I definitely favor this over this. I would call this a monstrosity, but maybe some people like it. Okay. Another Python 1.4 feature is a filter. Basically, again, filter is this higher order function, a function that takes a function as input or returns a function. And it's going to take some function that's a predicate function. A predicate function takes a value and returns true or false. So, and every item that this predicate returns true, it's going to keep. Otherwise, it will dump things that it doesn't return true for. So here I've got a simple predicate function, greater than or equal to 0. So 0 is greater than or equal to 0. That returns true. It's going to keep that. -1, that would return false. It will drop that. 3 and 4 are greater than or equal to 0. -2 it would return false. So I get something like that. So it basically filters out a sequence and materializes the results. And again, in Python 3, one of the notions of Python 3 is laziness. In Python 3, filter doesn't return a materialized list. So again, there's good and bad about this. One of the nice things about Python 3 is now you can filter infinite sequences if you want to. Take a long time in Python 2 for that. If you want to do infinite sequences in Python 2, you can use the built-in I filter, which basically is the same as Python 3 filter. Okay, and here's an example in the standard library of using filter. Again, this is from tarfile. This is a method that gives you the info list. Remember we talked about getting the name list from the info list. And this is how info list is created. It says, I want you to filter over the members of tarfile, and if it's going to pass in those members into this function here, this is a predicate function, and it says, look at the type attribute of what's passed in, and if it's in this global regular types, return true, otherwise return false. And that's how it determines if something's in the info list or not. Okay, so in summary, functional programming in Python, some of the arguments that people made for removing these constructs in Python 3 is that reduce can be ugly, and most 90% of the time people were saying like reduce operator.add over some list, and you can say sum that list, and it's the same thing. Or people were saying a for loop is more clear for people who haven't had functional background than reduce, so writing stuff in for loops is clearer for some people. The other ideas behind taking these constructs out of Python 3 is that list comprehensions offer a superset of map and filter. So the mapping and filtering we can do with list comprehensions, so there's no need to leave those in there. Another complaint was that there's no tail call optimization in Python. So tail call optimization is an optimization of the compiler that allows you to sort of do indefinite recursive calls if your functions are call themselves as the last statement of the function. Okay, so now we're going to do an assignment, and the assignment is Hello World. So everyone should open your favorite editor and do something like this and just validate that your code works. And if people need help doing this, let me know. I'm available to help. Okay, so in here I've got this TPS drone guy. So I'm going to make a file called hello.py, and I'll open that. And I'm going to import, can you guys see this okay? Let's see here. So import TPS drone, I'll just say as TPS, and then I'll say D equals TPS drone, and D dot takeoff, and D dot land. Okay. Whoops.
So it pops up real quick, it does it, and then it goes up.
Yeah.
It works if you do it in the terminal.
Yeah, and it's, yeah.
So you put a state.
If you do it interactively in the terminal, yeah.
Okay, so I'll go to terminal here.
Like if you actually run Python and type it in
Oh.
or if you put all the sleeves in between so that you can see what's happening.
Okay, so we'll put some sleep in here. Import time dot sleep, 2 seconds.
You might want to put it between takeoff and land so you can actually see it bigger.
Oh, there it is. Okay, so. Jeez. Now the demo gods are like hating me. I'm sorry. I did this multiple times before.
Or you could just wait for like a keyboard press or something like that.
Yeah, it should get bigger and smaller. Let's see here. What is going on here? Okay, so I'll put in the time here. Let's see. 3. Okay, so it should do something like that. It should pop this up. If it's not doing that, then let me know. Does it do that for everyone or not?
I have the sleeps in, I can see it.
Okay, if you have the sleeps in, you can see it. Who else needs help?
Well, I was doing that.
Okay. Okay, so just some notes. I use spaces. Well, there isn't much assignments here. So if you look at my code, it uses spaces, not tabs. So that might be problematic if you're editing the code itself. Okay, so now after everyone's done hello, we're going to do this assignment. So use map to actually spin the drone around. So like I said, there are a few commands like so move left and actually turn, and there's turn. So what's the, let's see what it is here. Turn. Yeah, turn left and turn right. So there's move left, which moves the drone left, but there's also a turn. So we're going to use map to either call turn left or turn right. So take a few minutes and use our functional programming skills that we just learned about to do turning left and right. And I'll see if I can get this drone to map left and right.
Turn it left by a certain number of degrees.
Yeah, so one of the things about the interface to some of these drone libraries is that they're not, like I said, they're not super smart per se. They're meant for people to pick up their iPad and just start using. And so, like the Python library actually forked actually does have some notion of turning degrees, but for our purposes in this, just if you call turn left, it turns about 5 degrees per se. But when I was doing this with the kids, one of the issues we had was that the library I was using didn't have the notion of like turning right 90 degrees or turning left 90 degrees. So what we had to do is we actually had to take it off and say turn, and then keep calling turn, and then count how long it took to turn, and calibrate our own sort of notion of how fast the drone turns in. So we figure, this is actually sort of a silly story. So we took it off and we spun it around for 20 seconds, and we figured it took like 10 seconds to go 180 degrees. So we wrote a program that said, blast off the drone, go forward for 10 seconds, spin for 10 seconds to come back, and then come back this way. So we did that. We typed in the program and we launched it. It took up, it flew out, and then it started turning, and it turned like 90 degrees instead of 180 degrees and flew over the top of the school. And one of the weird things about this drone, or I think it's sort of weird, is that once it gets out of range, it just hovers.
Wow.
Yeah. So it just was sort of sitting there on top of the school, and then we had to go over and chase it, and it was a harrowing moment. Anyway. Okay, so I just did with mine, I did hello, where it just took off and landed. That's with the drone. So I'm going to do a map guy here. So does anyone need help or hints on how to spin around with map? Okay. So one of the things is, so we want to say like d dot turn left, right? But we want to do that in a map statement. So I want to say like 20 times I want you to turn left, right? But this won't work here because map is a special kind of function. What kind of function is it? Higher order function. So what does it take as the first parameter? A function. So what should we pass in as the function? Turn left without that? Okay. Let's try this and see if it works. So I just made a function called mapper, so I'm just going to okay, so maybe it turned left. So let me see. Yeah, so this actually works on this because turn left takes star args here. If turn left didn't take star args, then I would have to do something like this. Lambda x, where it's going to take in this range number here. And I just ignore that, just drop it. And then inside of my lambda, I'm just going to call turn left. So let's try that. Okay. So that didn't look like it turned very much. One of the things, again, the interface to this isn't super. Are you guys making your turtles? Are you guys spun turtles that spin? No? Okay. Who wants help? I can come in and help someone if they want help.
I'm good, but I do have a request. Can you make it fly a little higher?
Fly higher. Oh boy. Yeah, let's try and do something. Oh, you want to take it off from the desk? I don't want to do that. That's gonna. Okay, if I chop up the ceiling here, no one tell the university. Yeah. You guys all signed the waiver, right? Okay.
Maybe just move it closer to the whiteboard. It'll be more clear.
Move it closer to the whiteboard? Okay, if we chew up the whiteboard here. Okay, let's see here. So here. So. Okay, it moved up a little bit. Let's make it move up more.
Out to the side, not behind the podium.
Oh. Okay. Over here?
Yes.
Sorry.
It's okay.
Okay, so basically it's not really moving around. So unlike yours, mine like basically you say move and it sort of moves a little bit. Whereas if you're controlling it with your iPhone or whatever, you're going to hold down that move and it's going to keep doing it. So we need to like put some delay in afterwards to make it be a little bit smarter. So I've actually written a function called map delay here that takes a function and a sequence and puts in a delay as well. So it will sort of actually do stuff. So instead of calling map here, with the built-in map, I'm going to call map delay, which is my map. So that's in the PS drone file. So it's called PS map delay. Let's see if this works better. Okay, it's moving somewhat. Okay, let's see here. Map delay, turn left. What's it doing here? Okay, so it's being finicky. I'm going to keep going while it's being finicky, and I'll debug later. Who has questions about this? Did you guys use a map to spin your turtle drone around? Yes? No? Who's no? Okay. So let's do this one. So in my library, I have TPS is my guy here. So I'll call map 2, and I'll say D is TPS, TPS drone, D dot takeoff, and I'm going to say map D dot turn left range 20. Okay, let's see if the demo gods will work with me here. Okay, so it says turn left takes exactly 1 argument, 2 given. So what's the problem there? Who got this error? Okay, so why is that happening?
You can't pass an argument to turn left.
Yeah, if we look at TPS turn left, I don't say it has any arguments. So I need to do that little lambda trick here. Okay, so lambda x, we're going to take in the range number, we're just going to ignore it, and we're going to call that. Okay, where'd this guy go? Okay. Okay, so here's my screen right here. It's turning left 20 times. Change this to 200. And it turns around like that. Okay. Who still needs help? Did everyone get it to spin around? Yes? Okay. I saw some smiles. Okay. We will keep moving on then. Okay, so I'm going to talk about context managers really quick just for the sake of my guy here, because if you didn't notice, I was using context manager. That's the with statement. This came out in Python 2.5. There's a PEP. PEP stands for Python Enhancement Proposal. So 3.4.3 describes context managers. Basically, what they allow you to do is they're a shortcut for try finally statements. Python supports, in addition to a try except, where there's an error, it supports optional finally statement, where that finally statement will always execute. And so I'm doing something like this, or sort of like this, where I'm saying, make a drone, do some flying with it, and then I want you to land. I want to make sure this guy lands at the end. I don't want him to, like, if there's an error, to like be flying up there for 20 minutes or whatever. So I want this drone to land at the end, and if I'm doing all these demos for you, it's annoying to type in these try finally statements all the time. So if you go to that guy's code that I linked to, the guy who's doing the master's thesis, this is like his hello world. It's actually something like this, where he imports the drone, he does startup, which connects to it, then he does reset. So one of the things, I don't know if you noticed, but there's like LED lights on the front here that like go green, if you can see them or not. If this crashes and like gets shaken up, then they go red. And if they go red, then it's like in fail mode until you tell it to reset, and then it goes green again. So if it like crashes on landing and goes into like this fail mode, it won't take off on the next time unless you reset it. So apparently he was crashing it a lot, so he always like reset it right after connecting to it. And then you have to do some silly thing like this while loop here, where it says, look at the data. So this guy has some data that you can read off. And one of those is this nested list here, 0, 2. If that's equal to 0, then it's still resetting. So sleep for 1/10 of a second until it finally resets, and then take off, and then wait for 7 seconds. And then finally, we get to like where we can sort of do stuff, and then land and shut down. So there's actually a fair amount of boilerplate here. So it'd be a lot better to, instead of like typing all of this, to do something like this with, like say, with flying as drone. So we see a colon after that drone there. What does colon mean in Python? Or what should you think of when you see colon in Python? Indent, this way, right? So anything that's indented in that context manager or that with statement is in what's called the block of the with statement. And when that dedent happens, when you pop out of that with statement, then there's some cleanup, or there's that the context manager allows you to define the finally execution code that will execute when that block exits. So after it exits, after this do stuff, I want to land and shut down, and I always want to land after I'm done with my code. And so this guy will allow me to do that. And it looks something like this. So one of the ways that you can define a context manager is to create a class that has a dunder enter method and a dunder exit method. Okay? So this dunder enter guy, if you squint at this code, it looks a lot like this code right here, right? All this stuff before do stuff is the enter. So that says, when I go into this with statement, this with block, before I give you access to it, I want you to execute all this, and I'm going to return self.d. So that as drone there, this is the self.d. It's returning that to me, so I have access to it within the block. Okay? And then when I dedent, or I'm done with flying around or whatever, every time I'm going to call this dunder exit guy here and say, I want to land that drone and I want you to reset it. So if he crashed or whatever, then he's good to go. And there's some other parameters here that talk about what the errors were thrown in the body, and we'll explain those later. But this is a simple context manager that allows me to fly the drone and do it with code like this, rather than typing this out every time I want to launch the drone. Okay? So, and if you look in PS drone here at the bottom, you'll see that context manager flying. And and that's what I was using to to do that. So, okay. Just briefly, because I was using Context Manager in my code to do this, I would introduce context managers. We'll come back to them in a bit because there's another way to specify context manager with a decorator and a generator. And since we haven't talked about those yet, I'm not going to talk about those until we talk about those. Let's dig into functions a little bit more. So one of the things that's interesting about a function in Python is that in Python, a function is an instance of a function. It's an actual object. And so when you define a function, if you look in your namespace, so here I'm defining a function foo, and it's got a docstring and some body that prints something. Inside of my interpreter, if I just type foo, but I don't call foo, I just type foo, it says you have function, and it's named foo, and it's located at some location. In Python 2, there's a built-in function called callable, and I can pass in some object into that, and Python will tell me whether or not I can call that function. In this case, foo is callable, so I can call it. And to invoke a function or method in Python, we just add in parentheses. So if I put those parentheses on the end, then it says invoke foo, rather than just saying function foo. A function also has attributes. It's an object, and objects have attributes in Python, or can have attributes. So a few of them, dunder name is actually the name of the function. Dunder doc is the docstring for the function. And if you want to find out more about attributes, there's a pep there that describes the attributes of a function. Another interesting thing is a function knows about itself. So inside of the body of this function here, foo2, I can print the dunder name attribute of foo2. So I call foo2 here, and I say print your dunder name attribute, and it says my name is foo2. Which might not be super interesting, but then we can do crazy stuff like this, where we can say, I'm defining a function, foo3, and I want you to print the stuff attribute of foo3. Well, nowhere is stuff defined at this point, but then afterwards I can come in here and say foo3.stuff equals data, and I can call foo3 and it prints data right there. So in addition to functions being objects, we can attach attributes to these functions as well. Okay, let's look at how parameters work a little bit more in functions. So we can have a function, so we define a function, it will have a name. We have various types of parameters. We can have default parameter, normal parameters here. We can have like default or named parameters. We can have variable parameters and variable keyword parameters. We'll dig into those a little bit. We see a colon, so again in Python we see colon, we think indent. Everything inside of that is the body of the function. It can have an optional docstring, and then it will have the implementation down here below. So as mentioned, Python has various parameter types for a function. You can have no parameters. You can have standard parameters or just normal parameters. You can have as many as you want. I think the limit is 256 on some versions of Python. You can have named or default or keyword parameters. You can have a variable parameter. You can have one of those, and it's preceded by a star. You can have variable keyword parameters, and those are preceded by two stars. So just to briefly review these, here I've got a function param func that has a normal parameter and two default parameters. I'm just going to print a list with the parameters in it. So I say param func 2. 2 comes in for A, and it prints 2. And B and C have default values. B defaults to 2, C defaults to 5, so I get 2, 2, 5. I call 3, 4, 5. I'm overriding A, B, and C, and it prints 3, 4, 5. And I can also change the order of them if I want to. I can say C is 4, B is 5, and A is 6, and print 6, 5, 4. Okay, so star args and star keyword args. Star args in a parameter definition will be a tuple of parameter values. Star keyword args will be a dictionary of name value pairs. And again, there's only one of each type, and this, the name args and the name KW args is just a convention that people use. So you don't have to use that in Python world, but if you don't, people might look at you weird because that's what people tend to use for the naming convention. So here's a function that has star args in it, and we'll just look at some invocations of that. I'm just going to print the type of the args here, and I'm going to print the args. So I call it with no arguments. It says the type is a tuple, and it's an empty tuple. I pass in one argument. The type is still a tuple, and it's a tuple with that argument in it, which is the integer 1. I pass in two parameters here, 3 in the string foo, and it still says it's a tuple, and it has 3 and foo in it. So this, if we say star args here, then inside of the function in the body, args without the star in front of it is a tuple with those parameters. Okay? If you put a star before a sequence on a function invocation, note this is a function definition up here, but if we're invoking a function and we put a star in front of a sequence, that does an unpacking or splat. So let's look at some examples of that. Again, I have this demo args function here, so it just prints out the type and the arguments here. I'm going to call it with, I've got a list here, args, that has 1, 2, and 3. I'm going to call it with those args, what's found at args0, args1, and args2. It prints out the 3 parameters here. Now, this invocation here, manually typing that out, is the same as putting the star in front of args here. So that star does what's called unpacking or splatting, and it takes this sequence here, and it's the same as passing in each of those parameters individually. Okay. Now the thing to be careful about that might get you is if you call demo args and you just pass in args there, but you don't put the star in front of it. What happens in that case? You still get a tuple as args, but it's only got one guy in it. And the only parameter it has in it is a list with those guys rather than them individually. Okay, so just a little bit more. Here I've got a function here that's got 3 normal parameters. I can call it like that. I can also unpack into normal parameters, but I have to make sure that I have all those parameters in a sequence. Okay, star keyword args. Here again, we just have a simple function that prints the type and what the arguments look like. I call it with no arguments, and it says it's a dictionary, it's an empty dictionary. And when I use keyword arguments, I have to provide a parameter name. So I have to say 1 equals 1. So there's a dictionary, the key is 1, it maps to the integer 1. 1, 2, I get a dictionary here. And note that this is arbitrary order because a dictionary in Python doesn't have an order. Similar to the unpacking in star, you can put 2 stars before a dictionary in an invocation, and that will unpack the dictionary or splat the dictionary. So here I've got a function that tells you the distance between 2 points. So it takes x1, y1, and x2, y2, and we're squaring the difference between those and taking the square root of them. Again, this is not fast NumPy scientific coding. This is pure Python, so don't hold that against me here. But that will compute the distance between those. And so if I've got a dictionary here that has points in it, x1, y1, x2, y2, I can invoke it like this, distance star points, and that's the same as unpacking those and calling those parameters like that. Any questions about parameter invocation or unpacking or splatting? Who here has written a function with star args or star keyword args before? Okay, so this is all review for you guys. Okay, so let's just throw it all together here. Here's a function that takes one normal parameter, one named parameter or default parameter, star args and star keyword args. I'm going to print those out. So it's going to print normal keyword star args and star keyword args. I'm going to make an args tuple with 1, 2, and 3, and a keywords dictionary with foo to 3 and bar to 4. If I invoke it like this, demo param star args star keyword args, note that what I unpack from star args here actually goes into normal, and then it goes into keyword args, and star args, or args within the body of the function is actually just a tuple with 2 in it. It's not this whole tuple here. So these args can migrate, and one of the things to remember is that this invocation here is the same as calling this invocation down here. So in this invocation down here, it's pretty clear that arg0 is going to go to normal and args1 is going to go to kw. It's not going, they're not all going to go into star args there.
So if args was longer than
Uh-huh.
Keep being non-keyword args.
Yeah, so the question was, what if args is longer than 3? What would happen? So what this allows you to do is have an arbitrary number of arguments there. So you could pass in 10 or 20 or 0, right? And it would just support that. And why that's useful, we'll see it in Decorators. It allows you to write a function that accepts any number of parameters. And so when you write a decorator, you can decorate a function that has any number of parameters. You can make a generic decorator and not have to worry about precisely how many arguments go into that decorator. Any other questions? Okay. And if you want more gory details, you can look on the Python reference for that. Okay, let's talk about closures in Python. Closures are one of those things that can be confusing to people. If you go to Wikipedia, you look at the definition, it says it's a first-class function with free variables that are bound by the lexical environment. And unless you've had like a CS degree, that might make your eyes roll over and just ignore stuff after that. I've got a definition here that's slightly longer, but hopefully it helps explain what's going on there. So in Python, functions can return new functions. We saw that functions can be first-class functions. They can take a function or return a new function. The inner function is a closure, and any variables that inner function accesses that aren't defined inside of that are called free variables. So that basically this inner function closes over the variables that are defined outside of it. That's where closure comes from. And one of the places where closures are used are in function decorators. So I've got a function here called addX that takes some x, and inside of it, it defines a new function, and it just returns that function. And if you look at what the function it returns takes a number, and it returns number plus x. So this x right here, inside of this inner function, is not declared inside of adder. So this is a free variable. The closure closes over it and looks outside of this scope here and finds that x is in the outer scope here and has access to it. So here I call addX with 5, and I assign that to add5. I look at add5, and it says add5 is now a function called adder. So it returned a function. This is a first-class function. It returns a new function. And if I invoke add5 and 10, 10 comes in here. I'm adding 10 plus what was x declared to be 5. So the 5 came in from this original invocation here. So I get 10 plus 5, and I get 15 here. And because Python supports stuff like duck typing, you can do silly things like this, add bang, where I say add x, and I pass in a string exclamation point, and then I call add bang with hello world, and it returns hello world with an exclamation point at the end. Okay, one thing to note here is that add5 has a name, a dunder name attribute, and it's adder, right? Because we returned a function, and the function we returned was named adder. Okay, so now we're going to write a function that takes a drone and a number, and this function should return a new function that moves forward that number of times when run. So we're going to use a closure to do this. So it'll take a few minutes to do that.
And by where you say a drone, that's a unique identifier for that.
That's a drone instance.
Okay.
Yeah. Yeah, I'll show an example. So people who are on Python 3, since a lot of you are, this is like a miracle. We'll use Python 3 over here. Okay. So we got a hello, I think. Okay, so Okay, so I've got a context manager here called flying that returns the turtle drone. So I should be able to say import, is that answers or hello? Okay, draw, complains about that, print. TPS drone. Okay, import TPS drone as TPS, and then D equals TPS TPS drone. Okay, there's my drone. Now I can say D dot takeoff. It makes it big, so it's taking off. So if I say map lambda x d dot turn left range 20, this is in Python 3, it just returns immediately. Because Python 3 map is lazy, it doesn't materialize, it doesn't iterate over anything until I actually iterate over it. So one quick way to do that is just to materialize it, so I can do that. Oops. My editor's here, weird, but I put a list around that. So a list just converts map into a list, and when I do that, then it actually materializes that and actually spins around. Okay. But if I just, in Python 3, if I just call map, it just returns immediately.
Does it just mean a move forward doesn't actually do anything?
Did you take off?
I can move left on the ground though.
Yeah, my Pithy implementation of turtle, oh, maybe it doesn't. See, it's got bugs all over the place, it's like real with bugs. Like, I think move forward, I don't allow you to do that unless you take off. But moving left, it'll like skid around the ground. Sorry. Feature. Okay. So let's see here.
Oh yes, that's what it was.
It was in the documentation. Okay, so let's do I'll make another one guy here. Okay, touch t answers dot py. Okay. Okay, def, and we'll call this closure. So the write a function that takes a drone and a number. Okay, so closure. I'm gonna def move forward. It takes a drone and some number, and it returns a new function. Oops. Return a new function that will move forward that number of times when run. So I'm just going to call this wrapper. Doesn't take any parameters. And it's going to go for I in range num d dot move forward. Then we need to return that wrapper function. So we'll test it here. We'll say d equals TPS drone d dot takeoff, and f equals move forward. We're going to pass in d, and we're going to say move forward 10 times. So f is a function right now. I'm going to invoke f, and Let's see if this works. Okay, so if I call closure here, does something like that. Okay. Did that make sense? Okay. Any questions about that? Not super useful. Again, this is sort of silly code, but you can imagine if I have more interesting logic other than moving forward in here, I want to parameterize that logic to do something specific, right? And say, today I'm moving forward 10, and I just write some loop that says move forward 10, and I embed that in my code. And then tomorrow my pointy-haired boss comes over, and he says, well, in addition to moving 10, I also need to move forward 12. And so at that point, you can say, okay, do I just copy and paste that code and put an extra 1, 2 at the end or whatever? Or you can use something like a closure to generate a new code object that's parameterized by the number your boss tells you to do. Okay. Any questions about closures? Okay. Let's dive into decorators a little bit. These came out in Python 2.4. There's the PEPs that describe them. And again, the interesting thing here in Python functions are first-class objects, and so you can pass them around. And so in addition to passing them around, you can wrap a function inside of another function to sort of change the behavior. You can change how the invocation happens, or what the invocation parameters are, or what the result is if you want to. So decorators, in short, allow you to modify the parameters to a function, modify the function itself. You don't actually need to call the function, or you can modify the results of the function. Some common uses for decorators are to cache something. If you've got a long-running result, you put a decorator around it that takes that result the first time it's run, throws it onto Redis or some database or something, and then the next time you call it, it queries and says, have I already run this? If so, look in Redis or wherever and get the result. Otherwise, calculate it and shove it back into Redis. Monkey patching standard I/O. So I've done this. If you've got a function that spits stuff out to standard out and you want to capture that, you can say, okay, before I call this function, I want to rebind what standard out's pointing to, and I want to point it to a file buffer instead, and have, when I call this function, have it, instead of spitting standard out into the screen, it's going to spit it into some buffer somewhere. And then after I'm done, I revert that change. JSONify, some web frameworks use this to ensure that the results are valid JSON. So they look at the results after a call and make sure that's valid JSON. And a common one is logging time in a function call. So this is sort of your canonical decorator where you say, before I call the function, I'm going to start a watch, and after I'm going to start another one. Decorator definition, again, looking at Wikipedia. Wikipedia has an interesting one. Allows behavior to be added to an individual object, either statically or dynamically, without affecting the behavior of objects from the same class. That's an okay definition. I'm going to throw in a really terse and maybe obscure one, but I think it's useful for our purposes. I'm going to call a decorator a callable that takes a callable and returns a callable. Okay? So, and we'll see why I do that here. So in Python, functions can take parameters and they can return output. And we have this notion of higher order functions where a function can return a new function, or a function can take a function as input and return some output. So what a decorator does is, a decorator is this function in the middle here. It takes a function as input and returns a new function. And normally what this new function looks like is it actually has wrapped this original function that's passed into it. What this allows you to do is, now that you have a wrapped function, when you invoke this decorated function, you have access to before you actually call that function and after you call that function. So you can tweak that insert logic there. Let's look at the identity decorator. This is the most basic decorator. So what did I say my definition of a decorator was? callable that takes a callable and returns a callable. So let's see if this meets that definition here. So idem, def idem, so idem is a callable, functions are callables, and it says it takes func, so presumably that's some function, but in Python it could not be, but if it is a function, then a function's coming in, and it's also returning that same function as output. So it's a callable that takes a callable and returns a callable. Again, this identity decorator isn't particularly interesting, but it illustrates our point. Okay, now I have a function here, add, that takes two parameters and returns the sum of them. I'm going to decorate add with idem decorator. So I'm going to rebind add. I'm going to say add equals idem add. So in here, add's going to come in, and we're just going to return it. So we're setting it to itself. It's essentially a no-op. And then I call add, and lo and behold, add still works, amazingly enough. Now we're going to tweak it slightly. Instead of returning this same function here, we're going to, inside of here, create a new function called wrapper that's going to take star args and star star keyword args. What does that tell us about the function? What's that? Exactly. It will work with arbitrary functions. It will take any number of inputs. Okay, inside of wrapper, we're going to invoke our original function with whatever parameters are called with it, and we're going to return that result. And we're just going to return the wrapper. So we've tweaked this idem. Instead of returning the original function, we're now returning another function that all it does is call the original function and returns the result. So very similar to the original function. Now let's wrap this guy again, and lo and behold, we get 7 here. Okay, so does this guy meet our definition of a decorator? A callable that takes a callable and returns a callable. If func is a callable indeed, then it does meet our definition, right? Okay, any questions about this? Does this help make decorators make sense? Maybe?
What would you use this for?
Okay, so the question is, what would you use this for? For this, there's nothing interesting, right? This is identity decorator. All it does is wrap it. But you can see these comments here, before and after. So in here, when I'm actually calling add down here, this is before I call the original function. So I have access in here to these parameters that the function's called with. I have access to 3 and 4 before the function's actually called. So like I said, if I was going to make a caching decorator here, in this case, I could inspect the arguments and say, have I already run this function, this expensive function that takes 10 minutes to run, or your simulation that takes 2 hours to run or 2 days? Have I already done this? If so, look up where I stored the results and return that. Otherwise, get the results, and then after, stick them into my cache, and then return the results. Does that make sense?
So, I mean, the power of this would be that you could wrap a whole bunch of different functions and reuse the code.
Uh-huh. Great point. So the point was made that the power of this is it allows you to reuse the code, wrap a whole bunch of different functions, because this supports arbitrary functions based on these arguments here. So if you wanted to have a caching function, right, it'd be sort of silly if you're like, okay, so I've got simulation 1 here. It takes 2 days to run. I'm going to put some caching logic right into the code. And then the next day you're like, oh, I've got simulation 1.2. I'm just going to copy that, and I'll copy and paste the whole thing. And then next day I've got simulation 1.3. I'll copy and paste and change some things and put it in there. Now I've got 3 copies of this caching code floating around, right? What happens if I have a bug in it? Or if I need to change where the caching code, the password to my database or whatever changes. I've got to change it in 3 places. So if I have a decorator that does all that for me and is generic, I only have 1 place I need to change. So it allows me to do code reuse and do best practices. Okay. Any other questions about that? A good question. I mean, this is a silly decorator, but it allows us to see that it allows us to get access to that function there.
So maybe I'm not fully understanding. So the before and the after, I mean, if you were writing from scratch, if you turned those into, say, functions that could do your cache checking, why not why do it as a decorator, which seems to create, to me, a more complicated structure? I guess that's what I'm trying to.
Why wouldn't you just embed that logic directly into your function?
Well, why not write a function that, does the before and does the after, and then just write it into all your functions when they're originally authored? Is it just that you can go back and
Because now your function that's doing simulation 1 doesn't have a single purpose. Its single purpose isn't to do simulation 1. Its purpose now is to do check the cache, then do simulation 1, then check cache, then store stuff in cache. And one of the tenets of good reusable code is that code or a function will do one thing and only one thing. And now you're conflating what the code does. You're saying run simulation. Well, run simulation no longer runs simulation. It also does check cache, run simulation, update cache.
Well, another place where I've used this is I've got Python functions I'm using to calculate stuff, but sometimes I want to send it to the web. So I can put a @JSONify, thing, so I can optionally convert things to JSON if I want to.
Another place where this uses by Lambda. Lambda JIT is a decorator that basically compiles your function. So there you have completely different functionality, right? The decorator actually is a compiler that returns a compiled object, which is completely independent of the logic that your function that it compiles is concerned.
Yeah, that would be sort of insane to embed the logic of numba every time.
Yeah.
But I can see the draw, right, where it's like, oh, this looks sort of complicated. Why don't I just stick that logic in there before and after? And that's a fine line that you're walking, because now you start testing something, and you've got to have a cache there beforehand. You've got to make sure that cache is up. You're adding complexity to your function by not having to do one thing. I'll also show some more examples, and maybe it will make sense, and we can talk about it some more. Okay, so here's a decorator that actually does something. This isn't the identity decorator here. So I've got a global variable here called call count, and what this decorator does is it's going to call how many times a function is count how many times a function is invoked. Okay, so what was my definition of decorator? A what? Callable. It takes a callable and returns a callable. Okay. So here I've got a callable count that takes a callable func and returns wrapper, returns a new callable. So inside of wrapper, when wrapper is called, it's going to say global call count, access the global call count, increment that by 1, and return the result of the original function. So this should count how many times my function's being called.
So wouldn't that be called on any time?
Okay, so someone's like 2 slides ahead of me. So
Okay, all right.
that's okay. Any time a function is called, call count will be updated, right? So not specifically generic right now. So here I've got a function, hello, doesn't do anything. I'm going to decorate it, so I say hello equals count hello. And now let's test it. I say hello, and I look at call count, and it says call count is 1. I call it again, and call count is 2. So Python also has some syntactic sugar, so I can decorate by putting @ in the decorator name before the actual the declaration of the function. This is decorating the hello function with count. This is equivalent to saying hello equals count hello after the declaration down here, like I was doing right here. So this is some syntactic sugar that Python has that allows you to decorate in line. Okay, notice that you don't put parens on this decorator here. If you put parentheses, it complains, and it says count takes exactly 1 argument, 0 is given, and basically if you put parentheses here, it's the same as saying hello equals invoking count and calling the invocation of that with hello. Okay, so there was a problem with count. I'll pay you later for telling me about my slide problems. Basically, the problem was that what? Was my count implementation generic? It was using a global variable. So anything I wrapped with that count implementation would also up that. So it worked. It worked in some case. If I want to know a global call count of total number of calls, that would work. So here's a better way we can do it. We can do something like this. We can attach data to this wrapper function that's generated on the fly when we decorate. So here I'm going to say count2. It's a function that takes a function and returns wrapper, returns a new function. So it meets our definition of a decorator. And after we declare our function, we're going to attach an attribute to the function called callCount, and we're going to set that equal to 0. So during the decoration time, we initialize this parameter to 0. And during invocation time, we update the attribute on ourself. And lo and behold, we decorate bar with this guy, call it twice. We look at his count. He says it's 2. We decorate snaz, call it once, and it says his count is 1. Okay, there's one more problem here. If we look at bar dunder name, you know, it would be nice if bar actually said bar, even though it's a horrible name, that it said bar, but it actually says wrapper. And bar actually had this horrible docstring, but if we inspect the docstring now, the docstring is no longer correct. The dunder doc attribute is empty because wrapper doesn't have a docstring in here. So if you want to have better decorators, you should update the dunder name and dunder doc attributes. And Python has a built-in decorator called functools.wraps that does that for you. And here's another way you can do it. You can just say, I'm going to update the wrapper dunder name to the original function name and the wrapper dunder doc to the original function doc. But if you just decorate the wrapper with functools, it does the same thing. It also updates the dunder module attribute. So we started off with the identity decorator, which is very simple. And at this point, we're now at this decorator template. So if I intentionally didn't show you this first, because if you look at this, this would probably like make your head spin or, I don't know, make you less tired than you are right now. But hopefully we can look at this now and hopefully we can somewhat grok it and make sense. So does this meet our definition of a decorator? Well, it's a callable that takes a callable, presumably, and returns a callable. And so it does meet our definition. This guy right here is another decorator, but what this guy is doing is all it's doing is saying, I want you to decorate this function here and take the function that's passed in and update those attributes, the dunder name and dunder doc. So that's what that's doing under the covers. If that's confusing, then you can think of it as doing something like this. It's doing slightly more than that, but in essence, that's what it's doing. And then you have your wrapper function that takes star args and star star keyword args. Why does it take star args and star star keyword args?
So it can take anything.
Yeah, so it's generic. Or, you know, it's possible to make decorators that aren't generic, but presumably it could decorate generic functions if you wanted to, or functions with different call parameters. And then you just insert your before invocation logic here and your after invocation logic here. Okay, and just an example from the standard library. We talked about context managers, and context managers use wraps. It's actually a decorator here. A context manager is a decorator in there. So takes a function and returns a new function. And here's a small example from Django. Django has some decorators that say, I want to ensure that this is a get view or a post view. And so you can use this require HTTP methods here. And inside it, this is actually a parameterized decorator. So inside of here is our decorator. It's a function that takes a function and returns a function. And here we're using a closure to parameterize this decorator. So this is you can see it's triply nested here. But hopefully we've talked about closures, we talked about decorators. What we're doing here is using a closure to parameterize this decorator by the HTTP methods that are passed into it. Okay, so just in summary, decorators allow you to modify arguments. You can modify the function. You don't have to call the function if you want to. You could just say, answer to all decorator, and it just returns 42, right? And your coworkers would hate you, but you could do that, right? I mean, you have access to whatever you want inside of that decorator. And you can have access to the results of function invocation. Okay, so right now it's 3 o'clock. We're going to take a 15-minute break, so you guys can go get food or whatever, stretch, get some fresh air or whatever you need to do. Take a 15-minute break, so we'll be back here at 3:20, and then we'll work on this assignment. You should have used a fuse to tie it on.
Yeah.
Okay, so let's take a few minutes, and so my janky implementation here, you know, like we noticed, like sometimes it won't move forward unless you take off, but it will skid around the side. So one thing that I do with this with my rail guy here is that when I run him, I print out what the battery life is. Because when the battery life gets below like 15%, then it just refuses to take off. So battery life's at like 53% right now. So to sort of make the turtle guy more like the real guy, the assignment is to create a decorator called use battery. And we're going to decorate some of the methods on the drone to, when you actually call the method, that it calls draw battery on it. So basically, the assignment here is write the decorator use battery and wrap the takeoff method to use battery. So I don't know if you've noticed, but like just taking this off sometimes will drain the battery like 2% or something. So we'll spend a few minutes writing a decorator, and hopefully now that we've talked about decorators a bit, you can make one that works. Okay, so this one tends to throw people. That's okay. Let's look at it here. So I'm in TPS drone here, and I need to make a decorator called draw battery. So I'm going to define it right before TPS drone here. So my decorator is going to be called draw battery. And what does a decorator take as a parameter? Function or callable. Okay, in this case we're going to decorate a method, but we'll call it func. And then it needs to return a new function, right? So I just call it wrapper, and wrapper takes star args and star keyword args. Why does it take star args and star keyword args? So it's somewhat generic. We'll just pass on the implementation here, and we'll return wrapper. Okay, so here's our basic decorator. Okay, so wrapper is going, and we want to wrap takeoff. So let's look for takeoff. Okay, so we want to come down here and we want to say draw battery. Okay, so now I've decorated that.
Method called draw battery. Did you want to use battery?
Whoops. Yeah, my bad. Okay, that's supposed to be use battery. So draw battery sucks the battery. Use battery is the decorator we use to suck call draw battery. Okay. Okay, so now we just need to fill out the implementation here. So we want to call the original function, right? And res equals func star args star keyword args. And we want to return res. So let's just see if this works here. Okay, so I've got this guy closure, so I'm going to call closure here and see if he runs. Okay, so closure ran, and he moved forward. So I'm still apparently I can take off, right, because he took off here. So let's go back into here. So I want to look at the nav data here. So d.nav data. I want to look at that before and after takeoff. Presumably, if I'm doing this right, inside of nav data I have battery calculations, and it should, after takeoff. Okay, so data says it's at 100 both times. So, okay, we got like our failing case here. Let's fix it so it doesn't fail. Okay, so we need to put some logic in here. What do we need to do in here? So the idea here is we call our original function, but this function should suck down the battery a little bit, right? So how do we call draw battery from here?
It's going to be self on the method.
Yeah, so it would normally be something like this, right? Self.drawBattery. But do we have a self here? So where do we get self? From arg0, okay? So what's happening here is in this case, we're not decorating a function, we're decorating a method. And methods normally have self as the first parameter. So that guy, self here, needs to be args0. Okay, so in this case, it's not super generic. It's meant to decorate a method and will sort of only work with a method. Let's try this and see if it works. Oh, whoops. Okay, so lo and behold, now when we look at our data, before we took off, it said it's 100, and after it's at 99. Okay, do you have any questions about that? We good on decorators somewhat? Okay, this is sort of tricky because it's decorating a method and we don't have a self, but hopefully the logic still makes sense. Okay, class decorators. So class decorators are different from decorators that are created with class instances or with classes. Class decorator, in this case, from this PEP and what came out in Python 2.6, is meant to decorate a class. When I defined a decorator as a callable that takes callable and returns a callable, a function is a callable, a lambda is a callable. How do we make a class a callable? What method do we have to implement on class to make it callable? Init will make it callable, yeah. What else? If we have an instance, how do we make an instance callable? There's a dunder call. So if you define a class and you define a dunder call method, you can put parentheses after the instance and it will call that method. A little weird, but basically, so I showed making decorators with functions, but you can make decorators with lambdas if you want to. You can make them with classes using the dunder init, the constructor. You can also make them with class instances using the dunder call. So that's for decorators. This is for class decorators, which are different. So a class decorator is a callable that takes a class and returns a new class. And here's a simple example here. Shout class. Shout class takes CLS as input. Inside of shout class, it defines this guy called shout, which takes as its first parameter self. What should that hint to you? If the first parameter is self. It's a method of the class. Yeah, it's a method. not to be confused with the @class method decorator. Okay, and so so we define this shout guide that looks like a function but takes self, so maybe it's a method. And then on the class that's passed in, we attach an attribute called shout to it, and we assign that to this shout function thing, and then we return the original class. Okay, and then we use our decorating syntactic sugar, and we say shout class, and we define a class called loud. It doesn't have any implementation, we just pass on it. Then we create an instance of loud, and lo and behold, loud now has a shout method that when we call that method, it prints out, it invokes this shout method, which says, look at your Dunder class, pull off your Dunder name attribute, and uppercase that and print that out. So basically, it's allowing you to take a class in and manipulate the class or add functionality to it. So when does this happen? So decoration occurs during the class definition time, not during the instance creation time. So there's sort of two times here. One is when you're defining the class, and the other one is when you're creating an instance of the class or calling the constructor. So decoration occurs when you're defining the class. So here I've just got another class decorator that's showing that print will be called during the declaration of the class, that's print before. And so in here we say print before, then we define our new method, we attach our new method and we return the class. We decorate timing, and it prints out before in there. So the reason I put this in here is so that you know that you have access to the class, you don't have access to an instance of it. So if you have attributes on an instance that aren't defined on the class itself, you wouldn't have access to those during the class decoration. Okay, a nice thing about class decorators is they work with subclasses as well. So I subclass timing with subtiming, and it has this new method as well. So even an example from the standard library, in Python 3.2, there inside the functools module, there's a class decorator called total ordering. And basically, Python has these magic methods or Dunder methods that allow you to declare whether something is greater than or less than something else. And you have less than, greater than, less than or equal, greater than or equal, and equal. So it's sort of silly to have to define all of those when if you only have less than and equals, the others are composed of all of those. So that's what this class decorator does, is that if you define the Dunder LT and Dunder EQ and decorate with functools total ordering, it will fill in the other ones for you that are missing. So that's a standard library example. We're going to skip this assignment right now, and we'll just keep moving on. And if we have time at the end, we'll do it. Because I don't really. Has anyone here ever used a class decorator before? Okay. I mean, they aren't super common in the wild, so we'll move on. And if there's time, we can, and people want to at the end, they can do that assignment. Okay. Let's talk about list comprehensions. These came out in Python 2, and again, list comprehensions are one of these features that people said, hey, we've got list comprehensions, so let's get rid of functional programming in Python. So let's see what the big hoopla is over list comprehensions. So it's pretty common to loop over some data and accumulate. And again, note that this isn't super fast scientific Python code. This is normal, pure Python code. So I'm not advocating replacing like your NumPy loops or whatever with this code, but when you're in pure Python land, this is how people do it. So I've got some sequence that goes from -10 up to, but not including 10. I make a results list that's empty. I iterate over my sequence, and if something's greater than or equal to 0, I'm going to append 2 times that to the result. And results should have a bunch of numbers at the end that are 2 times what was fed into it. And so a list comprehension basically allows you to do the same thing in a single line of code. So the top is the list comprehension. We say results equals square brackets 2 times x. So we're going to accumulate 2 times x. And we're going to loop over every x in sequence and only do 2 times x if x is greater than or equal to 0. So people who haven't used these before, they can be confusing. And a lot of people say, well, you can do a list comprehension, but the for loop makes sense to me, and the list comprehension looks like a bunch of Perl code. So why should I use a list comprehension? So let's go over the construction of how to create a list comprehension from a for loop, and maybe it will make more sense so you guys can read them if you're having trouble. So here's one way to construct a list comprehension. So if I know I'm going to accumulate something into a list, I just say results equals empty square brackets. And then I'm going to take my for loop and shove it in there without any colon. So my for loop here says for x in seek. I'm just going to stick that into there. Now,
That doesn't work in Python 2 at least. Or it wasn't working for me. No, I would put x for x in seek, but without leaving off the first x, I'm not getting it to work.
okay. So the comment is if I have x or seek equals range 10, x for x in seek.
Yeah, so that works, but without the first x for.
Okay, so the comment is that this doesn't work.
Just for x in seek.
Yeah, so this isn't valid syntax, okay? This here is how to do the construction from an accumulating loop into a list comprehension. So these two aren't valid Python code. This is just building up. So I stick in that for loop, speaking to a microphone. If I have a filter, I tack it on to the end. So notice I had a filter here. If x is greater than or equal to 0. I stick that on without the colon to the end. And then I want to put whatever I'm accumulating in front. In this case, I've got a typo. It's not 2 to the x, but it's 2 times x. So I put 2x to the front. And as noted, if you don't put that, what you're accumulating in the front, is not valid syntax. So you need to put that in there. Okay, so this is how you would go from this code right here to something like this. Okay? So and as you'll note, this is acting like a map and a filter, right? It's doing filtering with the ifs at the end there. And it's not just taking x, it's taking, this case, it's taking 2 to the x. But you could imagine that it could call any function on that. So it could behave as a map as well as a filter. So the if statement is optional. You don't need to have an if statement. You can just say, I want to go for x in x range 9. I want to take 2 times that, and you'll get this result. You can also nest them arbitrarily deep. So here I've got, on the bottom here, I've got 2 for loops that I'm nesting, say, to create some matrix or something. And I'm accumulating in nested this tuple of x and y. So what I do is I take my 2 for loops and I pull them out, I take out the colons, and whatever I'm accumulating, I stick in the front there. So I stick the x, y tuple in front. At this point, it's debatable whether the list comprehension is more readable than the for loops here. Once you start getting more than double nested list comprehensions, I think they start becoming harder to read, and I'd probably favor the nested for loops instead. So.
I've been told they execute faster, is that correct?
So execute faster. So I'll give my general response to executing faster. First, time it with what you're using. With some things, if you time with data sets that aren't similar to what you're using in general, you might get different timing results. Also, this isn't. They probably do execute slightly faster, but this isn't going to be something that's like, oh, Instagram changed their for loops from nested for loops to list comprehensions, and now they use 1/3 as many web servers because they did that. It's not going to be huge savings, but it might be percentiles, small percentiles.
This morning's tutorial, they actually timed it, and he was saying that like 4 or 5 years ago, they were much faster. Now it's a toss-up, and in some cases, the for loops wouldn't even, they'd be more optimized now.
Yeah.
That was something I was told years ago.
Yeah. So yeah, and you know, if you're using like Numba or something, right, it could be that Numba is smarter and can take more advantage of for loops and comprehensions. So again, I would, if this probably shouldn't be a bottleneck, and if it is, you probably have other issues to worry about if this is a bottleneck, right? Or you'd push it into like SciPy code or something like that.
It does produce an iterable, which is pretty cool.
Um,
An iterable?
An a list comprehension is iterable?
Yeah.
Yeah.
Into a function that took an iterable.
Yeah.
Faster, but that's memory.
Okay, so list comprehensions, as I mentioned, can act like map. So if I want to apply stir to a sequence, if you recall, we saw this at the top of when we started looking at this. We called map with stir on a range. Here we're doing this with the list comprehension. So we're accumulating the invocation of stir on x for every x in range 5. So now it's behaving as map. It can also act like filter. So we're going to say, I want to take x for every x in some sequence if x is greater than or equal to 0. So it acts as map and sequence. And here's an example from the Python standard library, again from the csv.py. It's saying, I want you to invoke the CHR on all the integers from range 0 up to, but not including 127, and that gives you all the ASCII characters. Okay, so we'll spend a few minutes here and use a list comprehension. So before we used a map to spin the drone around, now we'll use a list comprehension to spin the drone around. Okay, should I do this one or are we good? Want to see me do it? Okay, I'll take that as a sure. Okay. Okay, so use list comprehension to spin it around, list comp. So we'll take off our drone, and then we're going to say d dot turn left for x in range 200. Did it work? Let's see here. There it is. Oh, well, turn left. Okay, so I'm calling the attribute turn left 200 times, which is useless. So let's invoke the method 200 times. Ta-da! Okay, so similar to map, like list comprehension serves the same purpose as map. Any questions? Does anyone else do it different? Okay. Okay, let's talk about iteration in Python. Python has what's known as the iterator pattern or protocol. So it's declared in this PEP 234. Basically, when you have some sequence in Python, so we have a sequence foo bar baz, and we have some for x in sequence, do some body of a loop. This is equivalent to this Python code before. In CPython, it's happening in C code in the interpreter, but basically the logic is the same as this Python code here, where on the sequence we call the iter built-in function, and that gives us an iterator on a sequence. And then we go into this while true loop, and we say, try to call the next method on the iterator, and in Python 3, that's dunder next. And if that returns something, then you have your body of the loop before. If you call dunder next, or if you call next and it raises a stop iteration error, then break out of your loop because that indicates Python's basically hijacking the exception syntax to tell you that it's done iterating. So this is the iteration protocol. Again, when you iterate something over something, you call iter on it. That gives you an iterator for your sequence, and you repeatedly call next or dunder next until you get a stop iteration. And every time you call next, that will give you the next item of iteration. So let's try this out. You can try this out on code if you want to. You can do this in real life. You can say sequence equals foo and bar, and then you get the iterator on it. You say seek iter, call iter on the sequence. And now the seek iter guy should have a next method. You call next on it. It's going to return foo. You call next on it again. It should return bar. You call next on it again, and it's going to raise a stop iteration exception. So at this point, that's Python's indicating to you that this iterator is exhausted. There's nothing left in it. So if you want to make an object that behaves that you can iterate over, you need to follow this iteration protocol. So this is how you do it. You define an object. Again, this is Python 2, so I'm subclassing from object. But you don't have to in Python 3. So I define a method called dunder iter. So behind the covers, when iter's called, this iter built-in function, it's going to call dunder iter on the object that's passed into it. Okay, so here in this case, foo is self-iterable. It knows how to iterate over itself. So when I call iter, it's just going to return itself. And then self has a next method. So it's going to call next on self to return the next item. In Python 3, that would have to be dunder next. So here's an example to make a basic crippled range implementation using an object. So the range functionality in Python 2 says I'm going to start at 0 unless you provide me a start number, go up to but not including some end number, and use a step. This one's going to always start at 0, and it's going to end at the number before end. Okay, so I create, in my constructor, I just pass in the number after the final one, so end is equal to end, and I say I'm going to start at 0. Then I define a method called dunder iter, and it's just going to return self. So it's a self-iterable. This guy knows how to iterate over itself. Normally, some things in Python are self-iterators, some things aren't, like a list in Python doesn't iterate over itself. When you say iter on the list, it actually returns a separate object that's a list iterator object. Okay, so this guy knows how to get an iterator, and the iterator also has a next method. So when I call next, he's going to say, is my start attribute less than my end attribute? If so, my value is going to be whatever start is, increment start, and return your value. If it's not, then I raise stop iteration. And lo and behold, I throw this into a list comprehension. A list comprehension knows how to loop over things. It knows how to follow this iteration protocol. And my list comprehension materializes 0, 1, 2, 3 when invoked with range object 4. Any questions about that iteration protocol? Okay, here's a standard library example. Dictreader, again from CSV. So Dictreader, if you're not familiar with it, it takes a CSV file and returns rows of dictionaries mapping column names to values rather than just like tuples of a row. And so if you look at the implementation of Dictreader, you'll see that it has a dunder iter method and it returns self, so it's self-iterable, and it also has a next method. And we're not going to go over the logic of the next method, but basically next method returns a new dictionary for every row in the dictionary. Okay, so that's the iteration protocol. Any questions about that? Okay, now let's talk about generators. These came out in Python 2.3. Who here is, we have people who've used generators before, so this will be review for some of you. The notion behind generators is that functions that have a yield statement in them don't execute when you call them. They only execute when you iterate over them. And we'll see some examples of that. And generators are used to generate sequences on the fly, and they can be useful for lowering memory overhead. So some examples in the Python 2 world, range, which materializes everything into a list, versus xrange, which doesn't materialize, but only as you iterate over the results of xrange does it generate these numbers. There's a caveat that xrange actually is not a generator. It doesn't behave as a generator, but it's not implemented as a generator, but it has some similar characteristics. So generators, again, materialize as you iterate over them one at a time. So we talked about, I had an object that did my range that said up to but not including some number. Here's the generator version of that. I define a function called genRange, and it's going to take the number after the final one. So we're doing, again, Python tends to follow in Python land. It tends to follow this half-open interval where you include the starting number but up to but not including the final number. So the implementation of genRange creates cur, sets that equal to 0, and it says while cur is less than end, yield cur. Okay, so when you define this, Python looks at that and it says, you have this yield statement in there. I'm going to treat this as a generator rather than treating it as a function. So when you invoke it, it doesn't return anything. It only returns things as you iterate over it. Okay, and so as you iterate over this, if you call this and you iterate over it, it's going to return what cur is, and then you call next on it again, following this iteration protocol. And what the interesting thing about generators is that after they yield, they freeze their state. So you call next on it, it returns some number, and it freezes its state there. If you call next on it again, it resumes from where it left off. So it would return to that comment that says returns here next. It would increment count, go up and check its while loop again, and if cur was less than end, it would return again. Otherwise, it would break out, and if it breaks out, then by default, it sort of raises that stop iteration error for you. So here's just an example of sort of talking about what I just said. I create an instance of this. I call it, I say genRange4 is equal to gen. And if I look at gen, it's not holding a list. It says it's holding this generator object. So again, these follow the generator protocol or the iteration protocol. So if I say next on it, it will give me the first number in it. If I say next on it again, it will keep going until there's nothing left. And at that point, it raises this stop iteration. Okay, because list comprehensions and for loops understand this iteration protocol, you can stick in a generator in there because it behaves with this iteration protocol as well. So I can say for num in genRange2, and that works. I can materialize it into a list comprehension, and that works as well. One thing to be careful with is that generators have this notion of exhausting. Once you iterate to the end of a generator, it's done iterating, and if you try and iterate again, it will just say I'm an empty generator. It will just re-raise that stop iteration error. So in this case, there's an example here. I create a generator, genRange2. I materialize it into a list. And then I try and materialize it again, and I get an empty list. Because that generator is exhausted. When you try and call next on it again, it just keeps raising that stop iteration. And so you have to be careful. You can't reuse these things. You have to create a new instance and generate over it again. Sort of following this Unix philosophy of doing one thing and one thing well, you can make simple generators and then chain them together. So here's a generator that takes numbers that are greater than or equal to 0. Here's another generator that takes every other number in a sequence. And then there's some chaining logic there at the bottom to sort of connect them together, and a list comprehension to materialize the results. So it says, I want you to go from the numbers -5 to 5. I want you to take only the positive ones, and then I want you to skip every other positive one. Because they don't execute until you iterate over them, they don't execute when you invoke the generator, they can be tricky to debug. Okay? So if you try and step into it, when you call the generator without iterating over it, it won't do anything. Your debugger won't step into it. So that can be tricky to debug because you say, oh, I created a generator, but it's not calling any of my functionality. It's sort of similar to this map in Python 3 where it doesn't do anything until you actually materialize it. So because it follows the iteration protocol, you can actually use a generator inside of an object. And if you just yield from the dunder-iter method of an object, you can make an object that's iterable using a generator. So when should you use a list or a generator? General advice, if you need to repeatedly use data, you should use a list. If you have enough memory to hold all that data in memory, use a list. If you want to do negative slicing, you should use a list. You can't negative slice a generator. Some other hints for using generators is to make it peekable. There's various cookbook recipes for taking a generator and having a wrapper around it called a peeker that basically stores a buffer, and you can say peek and it will look at the next iteration guys to tell you what they are, but not iterate over them. I think I have an example in the slides of that. Another thing that might be tricky for if you're replacing lists with generators is that generators are always truthy in the Boolean context in Python, whereas empty list is falsy. So be careful with that. If you say if generator, that will always return true, versus if you say if list or some list, it only returns true if the list has some content in it. Similar to like the memory thing, sometimes it's useful to cache the results of a generator if you know that you have something in a generator but you need to keep using those results. You might want to materialize those into a list or keep the last, a sliding window of the last couple of them. And another hint is if you have a function that's a generator and it's recursive, you need to make sure that you iterate over the results of the recursion, not just return the results of the recursion. And there's an example in the slides here about that. A few more hints. Follow the Unix philosophy of making simple generators and then chain them together rather than making one long, complicated one. Some other hints. I ran into this problem. Sometimes fetching one thing or materializing one thing is slow. An example is like a database call. So if you're fetching one item from the database at a time, that can be slow because you've got latency of your network connection there. So, but assume that you have a big query set that you want to return. You don't have enough memory to hold the whole thing. So you can fetch it one at a time. Another thing you can do is you can chunk it. You can say, I have enough memory to hold 30,000 rows, so pull down those initial 30,000 rows, generate over that. When I'm done generating over that, pull down another 30,000 rows. And then you only pay for that network latency a few times rather than every time. The built-in library itertools is useful in Python. It allows you to slice generators with positive slices, but not negative. Okay, I mentioned that xrange is not a generator. It behaves somewhat differently. This is Python 2. For Python 3, this would be range. So xrange, you can index directly, but you can't slice it. Xrange has no next method. So it's not an iterable, and it doesn't exhaust. So you can repeatedly loop over xrange, and it will keep giving you start over at the start when you loop over it again, different from generators. Okay, standard library example. Here's in collections.py, there's what's called the ordered dictionary, which is a dictionary that remembers the order that you stick things into them, and it uses a generator here to implement iter items. So it says, I'm going to call, for k in self, I'm going to iterate over myself, and I'm just going to yield k and self.k, that tuple. Okay, so take a few minutes here and do this guy. So make two infinite generators, forward and right. These generators take a drone, and when they're iterated over, they move it forward or right. So after you've implemented these two generators, then make some code like this that says like f equals forward drone and r equals right drone, and then call those some number of times in a loop or something. So materialize those generators. So we'll take a few minutes and work on that.
Some more common uses of capital method actually have.
Okay, let's look at this generator stuff. Generators can be confusing, so I'll just make a simple generator here. Call it Gen 1. And yield, we're going to say print hello, print by yield 2, print foo, yield 3. Okay, so down here, I just executed this code at the top, right? This is a generator. When Python sees it, it sees, when Python parses that, it says, you've got yield statements in there. I'm not going to treat it as a function. I'm going to treat it as a generator. I only execute it when you iterate over it. And so I can say, for I in Gen 1 pass. So I'm iterating over it, and it should print out my guys. Okay, so it prints out hello, bye, and foo. I can also say G equals Gen 1. And when I do that, I look at G, it's this generator guy. Notice that it didn't print hello. It didn't print bye or foo, right? I just have this generator here, and I can call the built-in function next on my generator. And at that point, it says, okay, now you're iterating over it. I'm going to execute that. And it prints out hello. Can you guys see that okay? Sorry, it's at the bottom of the screen here. I'll move it up some. It prints out hello and what it returned 1. Now when I called again, at this point, a generator, like I said, the Python generator freezes execution. It remembers where it was. And when I iterate over it again, it's going to continue right where it left off, which is that line following yield 1. So if I call next again, it continues where it was, and it prints bye and returns 2. So it freezes its state, and when you go back, it picks it back up. I call it again. What's it going to do? Yeah, foo3. Okay? Do it again. What's it going to do? Stop iteration. Okay. Does that help make sense a little bit more about what generators are doing? Maybe? Let's look at this one. So I make a generator that says forward, that takes a drone, and it's just going to infinitely move forward. Okay. Right, that takes a drone, and wall 1 or wall true, d dot move right. Was it right or turn right? Oh, I do have to have a yield. Yeah, so these aren't generators. If I did this, if I ran this, it would just run forever, right? So thank you, my virtual compilers. It's good. That's a good skill to have at 4:30 after 7 hours of like sitting in here listening to people drone on about drones. Okay. The question is, do I need a wall true? Do I need a wall true?
Yes.
What happens if I don't have a wall true? Then it will yield it once. I call next again. What will happen on it when I call next on again? Stop iteration. So to be infinite, I do need that wall true. Okay, so then I'm going to do some def. We'll call this gen test, and I need to get a drone, and I'm going to say f equals forward d, r equals right d, for I in range 72. And next F. Notice I'm not iterating over, I'm not calling the generator and iterating over it directly. I'm not saying for X in forward, because that would iterate forever, right? I'm using the generator protocol to call it next on it 72 times. Okay, let's see if this works. Cross your fingers. My virtual compilers did their job. Ta-da! Okay. Cool. Okay, did anyone else get that on their screen? Okay, cool. Questions about generators?
Mine went like that down the screen. Yes,
Uh-oh, people's did zigzags. Did you do turn right or move right? That's okay, we can do move right. Let's see what happens when it does move right. That's probably the better way. Like that?
Yeah.
Okay. Some people are more square, some are circular, whatever.
What are the units on this movement? How did you know 72 would make a complete circle?
Because I'm the boss. Yeah. Yeah, I think it moves 5 degrees or something. Yeah, it's sort of arbitrary. Like as you could tell, like when I was moving this guy and I said move X amount, it's sort of like I have to put delay after it, and it's sort of arbitrary about how much it moves. So it's somewhat simulates this drone, somewhat not, but okay. Any other questions? Okay. Do we feel like we understand generators slightly more, or are we just confused? It's too late in the afternoon. Yeah, too late in the afternoon. Sorry. Okay. Okay, let's keep diving down the rabbit hole. Generator expressions. So generator expressions are like list comprehensions, except they don't materialize like list comprehensions. So they use the list comprehension syntax, except they materialize as you iterate over them like generators. So instead of using square brackets, we use parentheses, and that changes a list comprehension to a generator expression. Okay, so here's some examples. On the top, I have my list comprehension. It's taking the square for every number from 0 up to, but not including 5. And on the bottom, I'm doing it with a generator expression. So I just replace those square brackets with parentheses. And notice that it doesn't return, what it returns is a generator object, right? It's not materialized, it just says you have a generator there. And generators follow the iterator protocol that we talked about. So let's use that generator. We throw into list, which materializes. And when we throw into list, it materializes into the same thing as the list comprehension. One thing to note that might be weird is that I don't have to put parentheses around the generator expression if it's the sole parameter into a function. So I'm calling list here, and I don't have to put extra parentheses around the generator expression in there. I could, and it would work too, but I don't have to if it's the only parameter to that function. Okay? Clear as mud? Okay, good. I like that. I ask ambiguous questions and get mumbling. It's great. Okay. So here's some more examples here. So I have numbers is equal x range from -5 to 5. I'm going to feed this sequence of numbers into this positive generator expression here. So I'm going to say x for x in nums if x greater than or equal to 0. Here, a generator expression is acting like a filter, right? It's saying take the numbers in the sequence that are greater than or equal to 0. In this skip guy, I'm saying I want you to take x for ix and enumerate pos if I'm in an even position. Okay, so skip says take stuff that's in an even position, and then I materialize skip. At that point, the generator expression executes, and I get my results. So if you found generators confusing, but you liked list comprehensions, basically you can use generator expressions to implement the same thing that generators do. Let's look at some examples. So on the top is a generator that takes in a sequence and yields everything that's positive or greater than or equal to 0. On the second is the same code, but it's using a generator expression to do the same thing. So it's returning a generator expression that takes that same sequence and says, I want you to return this generator expression with x only if x is greater than or equal to 0. And if we materialize them both, it says that they return the same results. So, you know, if the first one, generator, is confusing, but you like list comprehensions, they can behave similarly there. And here's an example from the standard library from string.py, cap words. It uses a generator expression there on the bottom. It says, I want you to join with either sep or a space. And we're calling join, and we're passing in a generator expression there. X.capitalize for x and s.split sep. And again, if it's the sole argument to a invocation, you don't need to put extra parentheses around that. You can, but you don't need to. So I guess they wanted to not make it look too much like Lisp, and so they made those parentheses optional there. Okay, any questions about those? Okay. Let's look at context managers. So context managers came out in Python 2.5. We've seen them, like I mentioned them briefly beforehand. Let's dive into them a little bit more now. These are a shortcut for try finally statements. So again, if I've got some code that says do some setup, have some body that I want to do, and then make sure you clean up at the end, it's nicer if I can just do it with one line rather than multiple lines there of setup and boilerplate for teardown. Okay, so here's some questions for you. What does this code do? No cheating. Okay, who thinks it returns 1? Okay, who thinks it returns 2? Who's too tired to care? Okay, good. Honesty, we like that. It returns 2. Okay, so apparently that finally beats the try. Okay, what does this code do? Try to divide 1 by 0 or return 2. Who thinks it tries to divide 1 by 0 and raises division by 0? Okay, a few of you. Who thinks it returns 2? Okay, and we've got our people who are abstaining from voting. We will ignore you for now. Okay, it returns 2. Okay, what does this code do? Raise an error or return 2? Who thinks it raises an error? Okay. Why not? Ah, I like it. Who thinks it returns 2? Oh, wow. People are getting the picture. Okay, returns 2. Am I trying to trick you? So the takeaway here is 2 is the answer. No. Finally always runs unless there's an infinite loop in here. So if there's some infinite loop in that try, it'd take a long time for finally to get there.
All right, but why didn't it, I mean, especially with the return one, why doesn't it do both?
Why doesn't it return both?
Yeah.
So what you invoke foo and it says 1, 2, as in a tuple, or in an alternate universe there's a 1 returned and 2 and.
No, I was not thinking of a tuple.
They're quantumly entangled.
So logically, what's happening is looking at finally first?
Basically, the interpreter under the covers is saying there's a finally there. I don't care whatever else is happening. I'm going to make sure finally runs, and if finally returns, that's what I'm going to return.
So it says finally has to execute, takes priority.
Yeah, finally takes priority. Yeah, question?
So will it actually execute, like if you have an expression in that return 1 that changes state, will that return 1 get executed and then it goes to the finally and does its stuff? Or does it just
Doesn't look like it.
call the return?
It just always suppresses that.
So the question is, if we've got something like this,
If you put a print statement in the try, you won't see anything come out.
okay, so we'll try it out here. So you're going to say like def try test, try, and what do you want to do? Print something?
Like return, no, you want to do a return,
So you want to return some invocation,
some expression that changes state.
def foo, and foo prints out hello, right?
Sure.
Okay. we return foo, and finally return 2, because 2 is the answer, right? So, should this print hello or not?
Yes, that's the question.
Who thinks it will print hello? A couple of you? Okay. Who thinks it will return true 2? Okay. Okay, try test. Okay. So it does execute that, right? But then it says, hey, you've also got a finally in there.
I gotta run that before I return.
You got to make sure I get my finally in, right?
So it
So
kind
that
of
finally-
overrides the return.
The comment was it overrides the return, yes. Yeah.
And that finally didn't have to have a return, and if it didn't, it would just return hello, the function, you know, whatever.
Yeah, so there is a return here, right? If there isn't a return here, just a print. So it returns hello, or prints hello. Well, let's do a return here. Well, we'll say this. R equals try test. Print R. So R is none, so it returned none, right? But which is what foo returned. But it also printed hi. So it makes sure that finally gets inserted in there.
But after the expression has been evaluated.
Mm-hmm. Yep.
This sounds like a bad idea, unless you want to suppress every.
Try, accept, and then finally.
So you've only seen it with try, except, and finally?
Yeah, that's actually useful though.
Oh, you're saying that try finally is not useful? You're offending try finally? His feelings are hurt. Yeah, so normally you see it with try, except, finally, right? But I think there are legitimate reasons for finally, but the takeaway here is that finally wins, right? It trumps all. Even though there may be side effects, code might get executed, exceptions might try to get raised, that sort of thing. If there's a finally there, you got to be careful because the finally is going to take all. Okay, so we've seen context managers, or presumably you have. You can open files like this. You can say fn equals open temp.foo, and then you can say fn.close. But it's better to make sure you close your files. Your mama doesn't work here, so your mom's not going to close them for you. If you use this with statement, you say with open as fn. You see a colon there. Remember, we think indent when we see colon in Python. So that the do something with fn is indented. As soon as that dedent happens, Python under the covers will clean up that code for you. Okay, there are two ways to make context managers. One is with a class, and we saw that. I made a context manager for taking the drone off and landing him. Another one is using a generator that's decorated. So that's why this is at the end, because we've talked about generators and decorators, and that's one way to make a context manager. Okay, context managers can optionally return something. They can use an as statement to return something. We saw that with the drone. Here's an example from the PEP. If you have multi-threaded code, it's common to acquire a lock, and then when you're done with that lock, you want to make sure you release it so you don't have a deadlock, so someone's not waiting forever to get that access to that lock. So code should look something like this. Lock acquire, do some code while you're locked, and then finally release your lock. Whoops. So unless there's an infinite loop in there, you should release your lock, because finally always wins. But wouldn't it be better to write something like this, with locked my lock, and when it enters that block, it takes the lock, and when it exits that block, the lock is released. Okay, so that's what the context manager allows you to do. And this is how you would implement that. This is right out of the PEP. When you say dunder enter, you acquire your lock, and on the dunder exit, you release your lock. Okay, so that's the class way to do it. If you want to do it the other way, you can use this decorated generator. So you say def locked, it takes a lock, it acquires it, and then you say try yield. When you say yield, that says I'm letting the body execute, let the body execute, and then when the body dedents, it goes into that finally and does whatever is in the finally there. So you can think of this as your enter up here, and this is your exit right down here. Okay, so you can return stuff. So sometimes, like the lock didn't return anything, but files have an as fn. So if you want to return something from your dunder enter, you return something, or instead of just yielding nothing, you yield an object. Okay. Error handling. So in your generators, you can use a bare raise inside the finally to deal with the errors there. In your class, you can return true, and that means you swallow the errors. Otherwise, so in your exit logic, if you say return true, that means it doesn't care about errors that happens. Also, the arguments to the exit, dunder exit, if there is an error, that will be the class, the instance, and the traceback. Those are those arguments to the error guide: type, value, and traceback. So you can, if there is inside of your body, if there is an error, you can inspect that, and you can handle it appropriately if you want to. Okay, so just error handling. Type is the class of the exception, value is the instance of it, traceback is where it happened, and if you return true, then it will swallow the exception. Okay, so here's an example of a database rolling back something. You might have a transaction where you say, I'm going to start a transaction, I'm going to run some database code. If there's an error in it, I want to roll back, otherwise I want to commit. So here you have something like this. Try to yield, try something. If you get any error, I'm going to roll that back, and I'm going to say raise there. That raise there raises the original error at the location it happened, so you know where the error actually happened, but you make sure you get in that rollback beforehand. Otherwise, you commit it. And this would be the class way to do that. So if we had an if type, and you see in your dunder exit there, if type is defined, that means you actually got an error, so I'm going to do a rollback, and I'm going to return false. That means don't swallow my exception. Otherwise, I'm going to commit my database, and I'm going to return true. There wasn't an exception, so I'm swallowing nothing there. Okay, so where are these useful? For managing external resources. So if you've got a file or a database connection for transactions, acquiring locks, we saw that. If you want to make sure you're doing some cleaning up afterwards, I've used it in previous work for, we had some code that needed to have certain kernel modules loaded to do some testing. And so we would load and unload these kernel modules, so we put those in with statements to make sure that those were loaded and unloaded at appropriate time. And people have hijacked them for cool stuff like generating HTML and XML. Here's an example from temp file. That's a standard library module that makes a temporary file. And you can see here it has a dunder enter that says if your file is closed, I want you to raise an exception, otherwise return yourself. And when you exit, just make sure that you close your file. Okay, so this is our last assignment, write a context manager that has a drone and launches it, but we're at the end here. So if you want to stick around and do that, I'll stick around for however long people want to. If people want to actually write code that runs on the drone, we can do that. Anyway, I hope this has been useful. Hope you guys feel like you can do decorators and generators and context managers and understand iteration and maybe functional programming. Thank you for coming. Have a wonderful conference. Yeah, thank you.